Chapter 4, Artifacts and Harm. In this chapter, we want to emphasize the way in which ethics enters into the design process right from the beginning. So rather than looking, as we did in the previous chapters, on how artifacts can influence outcomes, in other words, how artifacts can harm after they're done, I want to show how ethical considerations can come in right from the start. So what the book uses is the stovetop example. So the stovetop examples are ones in which an engineering class or an engineering student is asked to design a stovetop. Now, one of the things that is already pre-established is that there will be 4 burners and 4 knobs in this sort of arrangement. So the question is, where ought each knob to correspond to each of the burners? So as you see here in the drawing, the left front knob could control the top burner or the back burner. Same goes for the next one, moving from left to right. Could control the front or back. When we get on the right side, now here again is an engineering decision. Which knob should control which burner? So this knob here could control the back or it can control the front, and the same with this far right knob. So the problem essentially is this. You design a stovetop which makes it easy to determine which knob controls which burner. So let's take the first consideration, burners and knobs, number 1. Now, in a standard stovetop, if we had no predetermined criteria, there are 24 possible combinations for the connections between burners and knobs. So that assumes, for example, that the 2 knobs on the left side don't control the 2 burners on the left side. So if the knobs on the left can control the knobs on the burners on the right, and vice versa, then you have 24 different possible combinations. Now we can cut that down because normally in the first design we establish, or most people assume, I think the natural assumption is that the knobs on the left will control only left burners, the knobs on the right will only control the right burners. So in fact, even before we get into the connection, we've already sort of assumed one design feature, and that is that the right knobs will control the right burners, the left knobs will control the left burners. Of course, that still leaves open the possibility, right? You could have the left knob to left front, left knob to rear front, right knob in the front here to the front, right knob into the back, and so forth and so on. So this leaves open a number of possibilities, and there doesn't seem to be anything intuitive about one connection over another. All right, so the question is, how should we design the stove? So when preparing for this lecture, when I was considering this sort of design, I asked myself, what does my own stove have? So I have a stove that has a similar layout, the exception that I actually have a 3rd burner in the middle, which is fairly easy. There's a knob that sits right in the center of my stove. And I asked myself, if I were to go down there right now and turn the left knob on my stove, what burner would it turn on? And for the life of me, I couldn't tell you which burner it would turn on. And in fact, I asked my wife, I went down to look at our stove to see which one was which, and I said to her, if you had to turn the stove on and you wanted to turn the left front burner on, which knob would you turn? And she actually didn't know. She guessed correctly, but actually didn't know. So on many stoves, as you note, there's that little diagram that they put right next to each of the knobs to tell you which burner controls which knob. So really there's nothing intuitive. But in the burners and knobs 1, the first example, we make at least the first assumption is that the left knobs control left burners, right knobs control right burners. Now, one alternative to the burners and knobs arrangement is to design a stovetop such that the burners are offset from one another. So in this case, rather than having the front and back left burners directly in line, by off-centering them, you give a better indication of which knob is going to correspond to which burner. So as we see here, this sort of what most I think would take to be the intuitive arrangement is the knob on the leftmost knob controls the burner that it's in line with. The next one over, also which burner it's in line with, and so forth and so on. So this seems like a natural sort of arrangement. But this is one alternative. So rather than a standard stovetop where everyone assumes 4 burners equally spaced, one in front or back of the other, one way to avoid the problem might be to rearrange the stovetop. Now, of course, this still leaves open for the engineer to decide whether or not the knobs are, in fact, connected to the burners in the way specified here. And that really is a value judgment. For some, that might be, no, I want to put them in a different pattern for some other reason. Maybe the connecting tubes. Maybe because we're using off-the-shelf parts, and it's easier to connect the middle burner here, or I should say the left burner, the left middle burner over here. Maybe it's easier to connect this one to the back burner because of the materials that we have, or something along those lines, or the wiring that we have. It's actually better because of the type of wire we use. Whatever, those sort of decisions are an engineering decision, and it's a value judgment. It's what the engineer values in the design. Now, of course, there's other sorts of variations we could do. So setting aside just our standard 4 burners, one in front or back of the other, or our offset burners as in variation 2. Variation 3 offers something different. Why don't we simply put the knobs closer to the burners? So in this arrangement, there seems to be a natural assumption that the burners in this case will correspond to the knob that's closest to them. So these back 2 knobs control the back 2, front 2 knobs control the front 2. Now this design also looks good, but there are other considerations. For example, there could be the cross, as a reading we'll talk about in a little bit. There could be changes in this for various reasons. The engineer could crisscross these. The other thing that could occur in this sort of arrangement is there's a safety issue. All right, so the question is, do I want to be extending my arm between these burners when turning burners on and off? So how much space in between here does there have to be to make it safe for me to go and put my hand near the flames or on the side, left and right? Notice in the other examples, the knobs are out in front, which means I don't come particularly close to the flame. So this poses the possibility of more of a safety hazard if you're not careful with extending your arm over the surface area of the stove. This also brings up questions of material use. Right? So how much more material would I need to use for a stovetop if I had to increase the distance between the burners and the knobs and give enough safe space for me to turn on and off the burners? So let's talk specifically about ethics in design. The stovetop problem is really an error-provocative design paradigm. So we mentioned a little bit with Flight 965 in the previous chapter, but a paradigm, and just to be clear, so for those who are not familiar with the term or unsure, a paradigm is an outstanding, clear, or typical example. So when we talk about the stovetop problem as an error-provocative design problem, we mean it's a common or typical example of how design can go wrong. So design problems, as we've said in the past, design problems underdetermine solutions. So if I say to you, design for me a stovetop with 4 burners, that doesn't tell me anything about the arrangements of knobs, the arrangement of burners. It doesn't tell me whether you favor people who are left-handed or whether you favor people who are right-handed. All of these things are underdetermined in the solution. That's left completely up to the engineer, which is why right from the beginning, certain assumptions are made, certain value judgments are brought in, certain ethical considerations are brought in. Some designs make more sense than others. And a design problem involves a complex of decisions in which any one decision can both constrain and open up new possibilities. So by making one decision about which knob is going to connect to another burner, that also opens up decisions or constrains decisions about other aspects of the design. So if the outside left knob, the left outside knob controls the front, then you might want to say, well, doesn't that in some way intuitively constrain the right outside to the right front? But that's not necessarily the case. Again, that's an intuitive leap, but it's also a value judgment on the engineer. It's an engineering decision. It's a design decision. So the choices we make in solving a design problem reflect our values, both moral and non-moral. So, for instance, if you're the type of person who favors function over form, if you say when I arrange my room, or when I design a workflow for myself, or when I design any engineering artifact that I happen to be working on, for me, it's the function has to define the form. For others, you might say I have more of an aesthetic sense, right? I want it to look pretty. I want it to look good. and then we'll figure out how to make it functional. So values can be aesthetic, which are non-moral. It might just be your choice of materials or look or paint or so forth. But there are also moral decisions that are being made here. Because if you're inconveniencing people, if there's a potential harm, even if it's a small harm. So for example, turning on the wrong knob each time on my stove might waste gas. That waste in gas on my stove means paying a little more in my gas bill, which causes me a harm. Now, it's not a terrible harm. I don't think it's the harm that rises to concern like I should be suing someone, but it definitely is an inconvenience, and it definitely does cost me something if I'm constantly turning on the wrong burner. I'm wasting energy. I'm wasting gas that I wouldn't otherwise have to waste if the knobs were properly labeled or the stovetop was arranged in a different way. Now, as I said, some values are ethical values, and that's when we're talking about design, when we talk about choices that are made. Some of the values that we see implemented in the design do reflect ethical values. And that might be, so for instance, if I'm a lazy engineer and I decide that I don't care about whether my stovetop is intuitive or not, then that disregard shows a lapse in my moral values or my ethical values. If I do something arbitrary that might cause harm to the person cooking on my stove. So an engineer's choice of a design really does reflect his or her values and character. It's not morally neutral. Your choice of what you design, how you design it, how it's built, and so forth. Some of those things we talked about in the previous chapter all reflect on you as an individual. And so this is where we get into the notion of virtue. And although we don't talk too much about virtue in this class, it's probably worth stopping for a moment, or at least pausing for a moment to talk about this. In an ethics class, in any ethics class, whether it's engineering ethics, business ethics, or just general ethics, we often focus on, in fact, in this course, we will be focusing on actions that are morally appropriate. So when we're talking about design choices, that's a form of action. But there's another element to morality, and that's the character or virtue element. I can talk to you about what's morally right and wrong, but I can't make you want to be moral. So virtue questions of character, are ones that deal with who you are as a person, what type of person you are. And in this case, in the context of this course, what type of engineer are you? Are you a conscientious engineer? Are you a virtuous engineer? Are you one that considers the people that will be using your product or your artifact? Even if that thing is something fairly unimportant, even if what you're designing is a toy for a Happy Meal, that's still some child somewhere is going to be using that. How easily will it break? Are the parts going to fall off and present a choking hazard? Do you care enough to use materials that are safe? So all of these things reflect what type of person you are. If you have the attitude that this is a job, I simply do what I'm told, that's all my responsibility is, then that might show a lack of character. Whereas if you're a conscientious engineer who says, look, I can't put something together at your price point because that would pose a harm to others. I can't do that. I'm not that kind of person. I'm not going to compromise my ethics, my value, or who I am just to meet some sort of standard that you've set. So virtue and character, the type of person you are, is really something that we can't teach. I can show you what the right course of action, I can show you what things you ought to be thinking about when you're making your engineering choices, but it's going to be up to you whether that's the type of person you want to be. Now, we look at the notion of virtue. It's quite possible that there were some lapses, as the book notes. So you notice from the reading, the author talks about his parents' stovetop, and that going to his parents' house, it seems to have the most unintuitive notion of a stove. So you look at the design here. This front left burner controls this front. This burner controls the back here, yet these are directly in line. The two right side burners are directly in line with the knobs. Now this seems to be an error-provocative design. Seems if I normally walk into the kitchen and use the burner on the right, anytime I'm going to the left, I'm going to make a mistake. This seems to sort of encourage operator error. And the friend stovetop, which again also seems like a counterintuitive design. Now maybe there was a reason. It's quite possible that the engineer thought to themselves, well, when you're holding a pot and turning the heat on at the same time, maybe this is a more logical design. But again, this seems to provoke errors. The idea that these two back burners would be crisscrossed where these two front aren't. So each of these designs showed just a bad design decision. And because that bad design decision also can lead to harm to the users, even if it's a minor harm, even if it means in the electric stove example in the reading that I turn a burner on and I waste some electricity and the stove gets hot, is it possible I could burn myself? Sure. I could put a kettle on one side, turn the burner on and think that it's heating up when in fact the other burner is heating up, and I go in and I put my hand on it by accident. Or I set something down on the stove not realizing the burner is hot initially. But both of these show examples of how the sort of choices an engineer makes can provoke harm or provoke mistakes in the operator, which can lead to harms. So one of the things we want to take away as we're going through, or one of the sort of an initial point or summary here, is that not choosing an error provocative design is the morally right thing to do. So when we're making engineering decisions, when you're making engineering decisions, if you see a design that is going to provoke errors, the morally right thing to do is to change that design. So to just quote from the reading, not making a mistake in putting a conception to paper and not choosing an error provocative design solution are the morally right things to do. And an engineer ought to get moral credit for making the right design choice and for executing the design solution properly, just as an engineer ought to be blamed morally for failing to execute a design solution properly or for choosing a design solution that will provoke errors. So the praise or blame, morally speaking, that you are entitled to as an engineer depends on whether or not you've chosen an error provocative design. So ethics and design. Stovetop problem as a paradigmatic example of error provocative design. So as we're going through the course, this is one of the examples you should be keeping in mind when we're talking about error provocative designs. This is the sort of common everyday design choices that can lead to errors. So to summarize, design problems under determined solutions. When we're given a design problem, there isn't any one given solution. Design problems involve complex decisions in which any one decision can both constrain and open up new possibilities. So when we make one choice, and those choices right from the beginning, as the reading wants to emphasize, are ethical decisions. The minute I make one choice that leads me down a road which can increase possibilities or also constrain possibilities, but it's still an ethical choice. Choices we make in a design problem reflect our values. It reflects the value of the person doing the design. Some of these values are also ethical. So here again, the distinction being made between moral and non-moral values. Non-moral values think of as aesthetic values. The look, whether it is a pleasing design, as opposed to ethical values, values that deal with right and wrong, harm or non-harm. So two ways that our choices reflect values. The artifact itself can reflect values. So when we're making an artifact, the resources used in the artifact are one aspect of the values, right? Whether we build the artifact out of cheap plastic, whether we build it out of more sturdy plastic, whether it's metal, aluminum, whether it'll rust, whether it won't rust, all of those things come into play. Also, what types of resources are we going to use, right? So if certain elements or metals are rare, if it means destruction into the environment in order to make this artifact. Expenditures of energy. So when we're designing an artifact, the question is how much energy it's going to take to produce that artifact. Is it extremely costly in terms of energy expenditure? And is the outcome worth it? So is the artifact, the expenditure of energy, counterbalanced by the good that the artifact is going to do? Or is it simply wasteful? And the ability to remanufacture, recycle. So in our design choices, depending on which materials we choose, and actually which design we choose, the ability to remanufacture, recycle, or even repair becomes a value. So I remember a few years ago, I had, to give an example of this, I had a VCR, and the VCR was having a problem. It wasn't ejecting the tape. So I took off the cover of the VCR, and I noticed that there was a missing belt, a tiny little belt that attached to the motor that kicked the VHS tape out of the VCR. And so when I noticed that the belt had frayed and come apart, I went to a repair shop and I bought the belt. I think the belt cost maybe $2. It looked like a tiny, actually thin, rounded rubber band, essentially. And so I went to replace the belt, but it turns out that the way in which the VCR had been designed, it was impossible to get access to the belt. You couldn't simply slide it over the motor. You actually had to take apart half of the VCR in order to get in and replace the belt. And to be honest, to this day, I've never repaired the VCR. Sitting on top of that VCR is a piece of tape with a little bag with a belt on it. And mainly it was because the engineer who had designed that VCR never anticipated the possibility that the belt might wear out that ejects the tape. So while I was able to get the tape out, the VCR couldn't be used because I still have this missing belt. So simply the choice of whether or not to make accessible parts that are liable to wear out, such as this little rubber band, reflects a value on the part of the engineer. That value may be that all these devices should be fixed by professionals. Another value might be, it might just simply have been overlooked. So the value was carelessness. Did I think about how this product would be used over time and how the normal wear and tear of it might require something as simple as replacing a tiny little rubber band? The causal effects of the article or the artifact are also where we see ethics in engineering. Once introduced in the world, it can cause harm. So whatever our artifact is. So again, we're looking at this paradigmatic example of the stovetop. Everybody uses stovetops, or at least most people use stoves. And once this design is put into place, this can cause harm. And artifacts, once they've made it to the final production, have become an artifact. Once the design has made it to artifact, these things can cause harm. So just as a sort of review, overall, the choice of a design solution reflects the character and moral values of the engineer. And engineers ought to avoid error-provocative designs and strive for the best design solutions. So we're actually offering something a little more here. We're not just saying you should have a minimally decent design or you should meet a minimal standard, but engineers ought to avoid error-provocative designs and strive for the best design solutions. And we'll talk more as we go in the course about what constitutes the best design solution and whether that's even an achievable goal, because that notion of maximizing the best design, is that even possible? Well, if you can't do something, so from a moral point of view, to say I can't do something implies that I don't have a moral obligation to do it. So this is a classic in ethics, the ought implies can. If I say to you that you ought to do something, that implies that you can do it. I can't hold you to an unreasonable standard or expectation, morally speaking. So engineers ought to avoid error-provocative designs and strive for the best design solution. As we'll see later in the course, we'll have to talk about what it means to strive for the best design solution.